More about intersections and families. Last time you guys had Professor Sands here. And you guys used the well-ordering property to, not the well-ordering, the Archimedean property to show one of these intersections was 0. And then you did some other examples of intersections of sets. So I'm going to tell you a theorem today, and then we'll prove some parts of it. So here's the theorem. So this is just about, so a lot of this class from here on out we'll have a lot of theorems of this nature where we're just going to give a bunch of properties and then check them. So so let this thing here, so AI for I and I, be an index family of sets. Of sets. And so we'll let B be a set. Okay, and we have the following properties. First is that if you take B and you intersect it, let's see if I'm going to do this right. Let's actually, this is not the one I want to state first. So if I take the intersection, a big intersection over all these sets here, this is going to be a subset of AJ for all J in the index set. Okay, so when so this thing is like, you're intersecting a bunch of sets, and in particular, this big intersection is going to be a subset of each member of the family. All right. Similarly, if you're going to take a big union, so we're going to get the opposite. For all J in I, AJ is going to be a subset of the big union of these guys. Okay? All right. So now the other two properties, so these are kind of some basic properties of unions and intersections. Here's another one. So if I take B and I, do I want to union it with an intersection or intersection with a union? There's two of them. I just want to get the numbering right. Okay? So I'm going to union it with an intersection. AI, like so. So this is going to be the intersection over I and I of AI intersect B. So you can distribute, or sorry, union. Okay, similarly, there's another property. So if I do B intersect a big union, we're going to get another distributive property. Okay, so this is just the union of the intersections. So this is saying that the intersection with the unions is the union of the intersections. And the previous one is that the union with the intersections is the intersections with the unions. Okay? All right, and then last, there's two properties of complements, which are the versions of De Morgan's laws for infinite families of sets. So if I take the complement of a union, this is the same thing as the intersection of the complement. And here, if I take the complement of a big union, or sorry, if I take a complement of a big intersection, I'm going to get a union of the complements. All right, so this is the statement that I want to talk about today. Yeah, complement, thank you. That should have a complement over it. All right, so let's do the proof of one of these properties. So I'm going to give two proofs. All right? So let's start with the proof of 4. Okay, so and then I'm going to leave some of the other ones as an exercise. So I'm going to do one of these, and then these two guys, you guys should be able to do on your own. Okay, so let's do the proof of 4. Okay, so I'm going to do two proofs. This first proof is going to be a short proof, and let's just write out what it means. Okay, so this proof, I'm going to write out what this set means and then manipulate it and show that it's equal to this set. Okay, so B intersect this big union. Okay, so this is the set of x such that x is an element of B and x is an element, let me just make some space here. X is an element of this big union. So that's the definition of an intersection. All right, now I'm going to write down the definition of unions. So big unions over index set go with universal or existential quantifiers, and the big intersections go with the for all quantifiers. Okay, so these goes with the e's, and the caps go with the upside down a's. All right. So this is the set of x such that x is an element of B, and there exists some I in I such that x is an element of AI. So that's the definition of the union over an index set that we gave previously. Okay, now we can use the following property. We can use, this is something we did at the very early on in the class, is that we talked about how conjunctions distribute over these quantifiers here, right? So this is the same thing as the set of x, such that, well, there exists an I in I, where x is an element of B and x is an element of AI. All right, so that's what that is. Okay, and then we remember that this conjunction here, when I do this and here, this is the same thing as an intersection. Okay, so that's the definition of what it means to intersect two sets. So there exists an I in I, such that x is an element of B intersect AI, like so. All right, and now we're doing this definition for union again. Okay, so but this time we're doing it backwards. So remember we used it here. We replaced this thing with there exists an I in I such that x is an element of AI. That's what it means to be an element of the union. Same thing here, except we're going to do it backwards. So this is saying this is the same thing as the union of I and I of B intersect AI. Okay, so that's the definition. And so we showed that these two sets are equal, exactly on the nose. Are there any questions? So let me remind you that at this stage here, right, we used the following property from the, I guess, the for the second to third line. All right, for the second line to the third line, we used the property that there exists some, let me use a different letter. I don't know, let's say J. Let's do this. P intersect, there exists some J such that Q of J, something like this. So this thing here is equivalent to, there exists some J such that P and Q of J. Okay, so we're just using this property of how ands distribute over the existential quantifiers. Okay, so let me make another remark here is that the proof for this one is very similar, right? Except for you're using for all quantifiers here, and you're using ors here. Okay, does that make sense? Okay. Let me give you another proof of 4. And this one's a little more long-winded. So another proof. So we want to show, that B intersect this big union is equal to the union we can show two things, right? We can show that B intersect this union is a subset of the union and the other way around, that this, we have this other subset inclusion. So this is like the go-to of when you try and prove two sets are equal. You show that they're both subsets of each other. Okay? So to do this, you show the way to set up the proof, you can set up two things. You'll set up the proof for this inclusion, and then you'll set up the proof for this inclusion. Okay, so let's do the proof for the first inclusion. Okay, so all right, so let's let X be an element of B intersect this union I, AI. Okay, so by definition, this means that X is an element of B and X is an element of this big union. By definition of the union, X is in this big union. So I'm just going to kind of like, okay, so it's what I'm going to do here is I'm going to write down, so essentially I'm just going to apply definitions over and over again, okay? And the only thing you really have to be careful of when doing these proofs is to just make sure you don't undo what you did, right? And there's pretty much only one thing you can do from one step to the next, okay? And so that's apply the definition of what you just did. So many proofs from here on out will be of this shape, right? Where it's just like, okay, you do this, and now we have to use a definition. And what's the definition we can use? We can use this definition. Okay, so let's apply this definition. So by definition of this, we have the following proposition that there exists some I in I such that, well, let me write it like this. There exists some I in I such that X is an element of AI. So let's call this thing star. This means star is equivalent to. So now I'm just taking it easy, and I'm writing down this one again with this definition. Okay, so so the star is equivalent to X is an element of B, and here there exists some I, an element of I, such that X is an element of AI. Okay, we can call this something like dagger. Okay? Or flower, or whatever you want to call it. Or you can give it a number. You can give it a Roman letter. It doesn't matter. Okay? So by the distributive rule, so this is for ands and existential quantifiers, right? Dagger is equivalent to the following, that there exists some I in I such that X is an element of B and X is an element of AI. Right? And so by definition of unions, Okay, so again, so here I just wrote this out the same way, and then I wrote this out using this definition. Okay, and then I used the distributive rule here to pull out this existential quantifier. Okay, and now this is again the definition of a union, right? Here's one instance where we applied the definition of a union. Here it is again. Okay, so but by the definition of union, we have X is an element of this union, B intersect AI. That's the definition of union. Okay, so this shows the first subset inclusion from here to here. How does the subset inclusion proof start? It starts with let X be in the thing that you want to show is a subset of the next thing. And it concludes by saying X is an element of the other part that you wanted to show is an element of. All right? Okay. Let's do the other inclusion. Okay, let's do this proof here. So how should this proof start? Yeah, so let X be an element of this, right? I yeah. All right? Okay. So now what do we do? What should I do now?
Expand the definition.
Yes, expand the definition. So by definition, this means so that there exists some I and I such that X is an element of B intersect AI. Now what am I going to say? So I'm doing these little bullet points to kind of keep these things logically independent, you know. So what could I do now?
Can you put the essential quantifier over, or like the intersection, you make that an and?
So yeah, so we can turn the intersection into an and, right? That's a great idea, right? And that's really the one thing that we can do. So by definition, X is an element of B intersect AI if and only if, that's what it means to be a definition, X is an element of B and X is an element of AI. So the above line, this means, and then I'll do it up here. So this means that so there exists some I, an element of I, such that X is an element of B and X is an element of AI. Right? Or maybe I could do it like that. Okay? So we're using here, we're taking this formula here, and then we broke up what B intersect AI means. It's just an and. All right. So what should I do now? I think you suggested it in your previous time. Now I'm going to use the distributive rule. Okay, so by the distributive rule, the above formula says, well, it is equivalent to, let's say, so there's not just one distributive rule, but by saying the distributive rule, I'm saying the distributive rule for existential quantifiers and the and conjunction is equivalent to X is an element of B and, right, there exists some I in I such that x is an element of AI. All right? Now we can convert this into sets. Okay? So this proposition, or this formula, is equivalent to, well, x is an element, or x is an element of B intersect this union of I and element of I, AI, like so. Okay, so that concludes the proof of the second part. Where do we start the proof of the second part? Here. Okay, and notice the shape of the proof. The shape of the proof has the same thing. Let x be an element of this. Then you just apply a series of definitions, right? And you conclude that x is an element of the thing that you want to show that it's in, right? So that's how you prove that one thing's a subset of another thing. Cool? Okay? So I guess we could end the proof by saying something like, since we proved, right, since we showed we have two subset inclusions, we are done. Right? So we showed that one was a subset of the other, and the other was a subset of the original thing. Right? And that's how you show that two sets are equal. Okay, which one was faster? The first one. The first one was faster, right? Because we could write it in a shorter way. But that maybe involves a little bit of trickery. So, this one's more like safe, right? But the other one's definitely faster, right? If you can do it. So maybe on a test, you can write it out like in the fast way. Is a good way to do it. But you'll get some practice, and you guys will develop how to write the proof on your own, and you'll see which way is fast for you. Okay. All right, so let's do another example. Any questions so far? All right, cool. Okay, so let me recall the claim 5. I'll do claim 5 now. Okay, so the fifth claim says that here, it said that the intersection, or the unions here, i's and elements of I, here, this is equal to the intersection AI bar like this. Okay, so this is this claim. Okay, so let's do the proof of this claim. Okay, so we will show that there's two subset inclusions. So we will show that this thing, I and I of AI bar, is a subset here of the intersection I and I, AI bar, and then I'll continue up on this line here, or this board. And then we will show the other way around, that the intersection of I and I of AI bar, or let's write it like this so that it's more clear when I write the, so when I write the different parts, so I can use the subset and superset. So by the way, this sign here is called the superset sign instead of a subset. Okay? AI bar. Okay. Okay, so we'll show these two things to show that these things are equal. Okay, so the proof of this one. All right, so how does this proof start? So you let x be an element of here. AI bar. Okay? So by definition, this means that x is not an element of the union of I and I, AI. Okay? So now we can convert this statement here into a quantifier statement. Okay? So here, of the union of I and element of I, AI bar, this is equivalent to the fact that there exists. So this is saying that there does not exist some I in I, right, such that x is an element of AI. All right. So this one here, this is equivalent, logically equivalent to, what do I do now, guys?
Distribute the not.
Yeah, distribute the not. And how do I do that? Reverse the quantifier and then negate this, right? For all I in I, x is, well, not an element of AI. Okay? And this statement here is equivalent to the following statement. It's equivalent to AI bar. For all I in I, x is an element of AI bar. Okay? So by definition, now what do I do here? So what am I going to say? By definition of intersection. So an element is the same as the intersection of AI bar. So that's the definition of the big intersection. Okay, so here we showed that, so here we started with x is an element of this thing, and then we showed that x is an element of the other thing that we wanted to show, which shows the first subset inclusion. Okay, so let's do the second proof. Okay, so here, well, here we really have the same thing, right? Right? It's essentially the same. So let's just do it. So let x be an element of this intersection, I, AI bar. Okay, so let's apply the definition. Okay, so this means that for all I and I, x is an element of AI bar. But x is an element of AI bar is the same thing as x is not an element of AI. So this gives so this means, well, so let's say for all I and I, x is not an element of AI. All right? And so now we can pull out, so this is again about reading the De Morgan's law both ways. So one way is about distributing negations. You can also pull out negations. Okay, and so for this one, we'll pull out negations. Okay, so this is equivalent to the following. So not for all I. So not that there exists an I in I such that x is an element of AI. All right? And this is the same thing as So the inside part is saying that x is an element of the union. So this is saying that x is not an element of the union here, like this, not an element of the union, which is the same as x being in the complement. Like so. Okay, so we proved this one, and we proved this one. So we have this proof here. Okay, we started with x in here, and then we showed that x was in here. Okay, and then here we did the same thing. Oh, except for we did it the other way. X is in here, then x is in here. And you can kind of see from this little argument here how you could write it out the short way. Okay? Okay? So let me just finish the proof. So to finish the proof, we'll just repeat what we just did. Okay? And this indicates that even if I messed up somewhere, right, I knew what I was trying to do. Okay? So since we showed the two subset inclusions, the sets must both be equal. The sets must be equal. Must be equal. All right, and that finishes the proof. Okay, does that make sense? Okay, so so I'm going to leave the other ones for you guys to try. But now what I want you guys to do is do this indexed, this handout on indexed unions and intersections. So exercises. Yeah. You need one? In unions. So you guys should be able to like fly through this one, okay? So when you get good at this, you should be able to just look at them and be able to do them almost instantaneously, okay? So that's how you know that you're up to par on this thing, okay? So you should be able to just look at these things and be like, ah, that's what it is, okay? All right, and now I'm going to come around and help you guys.